Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about the ideal gas equation. We're going to manipulate the ideal gas equation to calculate density and molar mass of a gas. We're also going to talk about how we can do stoichiometry using the ideal gas equation with a balanced chemical equation. And then we're also going to talk about Dalton's law of partial pressures. So let's get into this video. So the first thing we're going to talk about is the ideal gas equation. And an ideal gas is this theoretical perfect gas with no attraction or repulsive forces. And we'll talk about that in further videos. But we had these other named equations from the last previous video, where we had Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. So all of these laws share a term with one another, and we can relate all of these. And we saw that we had the combined gas equation, which we're isolating and we're keeping the number of moles constant. With the ideal gas equation, we can relate all of these. So we've got PV is equal to nRT. So we can calculate any one of these as long as we've got the other four values. R is this special constant called the gas constant, and there are many variations, but we're going to mainly use two when we're discussing the ideal gas equation in our videos. The most commonly used gas constant is 0.08206 liter atmosphere per mole Kelvin. And that constant is there to help us cancel out the units and linearize our data. So the ideal gas equation is what we can use to relate all of these different terms to each other. So there are some different things we can use the ideal gas equation to figure out. We can manipulate this and do algebra, and we can solve for some different things. So one thing that we may want to know about a gas is the density of the gas. And if you remember, density is equal to the mass over the volume. Well, the ideal gas equation, we don't have a mass term, but we do have a moles term. So if you remember back from a previous video, we can relate the number of moles to the mass by multiplying by the molar mass. So if we were to isolate the number of moles over the volume, that's going to be equal to the pressure divided by gas constant times temperature. And if we were to multiply by the molar mass, then you're going to have m over v, which is density, is going to be equal to the molar mass times the pressure divided by the gas constant times temperature. So all you have to do is do some algebra, rearrange, and set things equal to whatever you want to find. The other thing that we could do is find the molar mass of a gas. So all you're going to do is algebra again, and if you were to isolate m, big M, molar mass, that's going to be equal to the mass times gas constant times temperature divided by pressure times volume. And again, mass over volume is equal to density, so molar mass is also equal to the density times gas constant times temperature over the pressure. So you can do algebra and figure out whatever one of these terms that you want to do. So the next thing we can do with the ideal gas equation is do some stoichiometry like we did in a previous video. If we isolate the number of moles n is equal to the pressure times the volume divided by gas constant times temperature. So if you know the moles of a gas, you can use multimole ratio to figure out the moles of another solid. So if we had the case of sodium azide, which is in the steering wheel compartment of most vehicles, and that's what's going to decompose to form nitrogen gas and fill up your airbag in the case of an accident. So say we've got some mass of crystals, we could calculate the moles of those crystals, and then we could figure out the mole-to-mole ratio of the amount of crystals to the nitrogen gas it produced. And then from there, you can just plug that into the ideal gas equation and figure out the pressure, the volume, the temperature. It doesn't matter. All this is now relating this to stoichiometry. So this leads us to our next law, which is the Dalton's law of partial pressures. And what this states is that the total pressure inside of a container is going to be due to the partial pressures of each of the gas within the container. So if you have multiple gases that don't react, they're going to exert a force all by themselves, and they're going to act independent. And if each of those are going to exert a force, then the total force is going to be due to all of the gases pushing on that container. So P total is going to be equal to P1 plus P2 plus P3 for all of the gases that you have in the container. So the last thing we're going to talk about that relates to Dalton's law of partial pressure is the idea of a mole fraction. And we use Greek letter chi, which looks like a squiggly X, and that's going to represent our mole fraction. And the mole fraction is going to be the moles of one compound divided by the total number of moles within that container. So if we're talking about gases and we got three gases, Say we've got hydrogen, helium, and nitrogen, and we've got the pressure of hydrogen over the total pressure is going to be equal to the moles of hydrogen over the total number of moles. So this is a mole fraction. You're taking whatever pressure or molar value and dividing it by the total. And if we relate that to the ideal gas equation, nRT over V is equal to pressure. So when you go to use this equation, you can find the pressure of any gas by taking the mole fraction, or chi, and multiplying it by the total pressure. And that's going to give you the pressure of that individual gas. So again, it's just algebra 1. All you have to do is move around the terms and isolate whatever you want to solve for. So there it is, you guys. There's the video on ideal gas equation, the derivatives of that equation, Dalton's law of partial pressures, how we do stoichiometry with gases, and mole fraction. So if you enjoyed the video, if you found it useful, smash the like button, send it to your favorite university, send it to your favorite combustible fuel, and we'll see you in the next video.